Hi, I'm Nick Rood, and in this presentation, I hope to find out whether it's possible to predict box office revenue of a movie. And hopefully, this also earns me my last badge in the IBM Advanced Data Science course. Okay, let's begin. Well, as you know, the movie business is big business. Last year, the global ticket sales were good for, I think, almost $42 billion worldwide. So there's a lot of money to be made there. But making a movie is also expensive. If you look at Avatar, for instance, that was about $237 million to produce. And luckily for the producers, this was all earned back because the movie made more than $2 billion. But unfortunately, not all movies are that lucky. King Arthur, for instance, from Guy Ritchie, was about $175 million to produce, and well, the result was quite a loss. Now, of course, nobody likes to make a loss on his investment. So, from the industry, there's a lot of interest in models that will be able to predict a movie's profit uh, before it gets produced. And the aim of my project is to see if it is possible to make such a model. Well, no models without data. So I found this data set on Kaggle. And Kaggle is an online community where you can find all kind of open data sets that you can well use to practice your skills on. And the movie data set was part of a competition, and it consisted of 3,000 movies that you could use to build and validate a model. And once you thought your model was good enough, you could then use this model to make a prediction on the revenue of almost 4,400 unseen movies. And I mean unseen by the model, of course, not by the viewers. And this prediction was your entry into the competition. Yeah, why would we want to build such a model? Well, yeah, I guess not many people want to produce movies that no one is going to watch. And even fewer people would like to invest in a movie that will not make a profit or even a loss. So, from a commercial point of view, I can totally understand the need for a model in which you input things like cast, genre, spoken language, and that gives you profit as an output. From a creative point of view, do we get better movies from this? Well, that's another discussion. But okay, what models did I build? The problem that we're facing is a regression problem. So I first developed quite a simple linear regression model and compared that to the performance of a more sophisticated random forest regression model. And then both models were then compared with a deep learning solution, a sequential neural network. The model can be reproduced and used for new predictions if you use the four notebooks that I created. You can see the links to the notebooks here. It's quite small, but well, pause the video. And the whole process I followed and all decisions that I made are all documented in an architectural decision document. Regarding the architectural decisions, yeah, some decisions that I made during the whole process. And as I said, the data set that I used came from Kaggle, and what was a bit annoying was the fact that I couldn't find a way to load that data directly into a project on the IBM data platform. So I ended up just downloading the data and then uploading it into a project on the IBM platform. After that, accessing the data was easy. You just read it into a Jupyter notebook. And I used Spark, of course, because that's nice, because then you can use some SQL statements. And for the further exploration of the data and model development, I used the well-known libraries like Matplotlib and Scikit. And I did have to go back to SPS Modeler once, because for some reason it's very hard to get the feature importance in a linear model when you build it with Scikit. Then about the data itself, the data set used to build and train the models had 22 features, like the cast, the crew, the genre, the language that was spoken, and of course one target, the box office revenue. Based on the 22 features, I created 57 additional features, like release day or month based on the release date, the number of words in a movie title, but I also created a star, crew, and production power index about which I tell a little bit more later on. And yeah, in the dataset there were the usual annoyances with missing values or columns that were in a JSON format. But yeah, basically the biggest issue was in the distribution of the most important feature, budget, and the target revenue. Here you can see that both budget and revenue are heavily skewed. And I didn't hesitate to log transform budget, but wasn't sure if I needed to do that with the target as well. But since the whole idea behind a regression analysis is that the target variable is normally distributed, I did it anyway. And as you can see, after the transformation, the skewness was acceptable and the distribution looked, well, much more normal. Although that large bar in the budget still bothers me a little. As I said, besides some obvious features like release day or release quarter, I also made a star, crew, and production power index. And yeah, a star index. Why? Well, for instance, the movies that starred Samuel L. Jackson made over 6 billion, while the movies with Ryan Phillip only made 415 million. So if you were to if you had to pay for a movie, which actor would you cast? I would go for Samuel L. Jackson. The star index, the formula you can see here. It is the number of times that an actor or actress appeared in the database on or before the release date of the movie he played in, and that was summed over all actors in that movie, and then divided by the total number of cast members in the movie. And I did the same for the crew members and the production companies in the database. And yeah, you always hope, of course, that your extra features will help in getting a better prediction. And yeah, first glance at the correlation showed that all three indices had a positive correlation with revenue. Although, honestly, I thought that the correlation between the star power and revenue, which is 0.16, I thought that would have been a little bit higher. Okay, how was the performance of the models evaluated? I looked into 3 indicators. First, I looked at R squared. R squared had the proportional variance that can be explained by the features. That's the one I'm most familiar with, so I use that one, and it's pretty easy to understand. Because if R squared is 1, the features can make a perfect prediction. Is R squared 0, your features predict nothing. But there is some discussion whether R squared is a good measure of goodness of fit. So I also looked into the root mean squared error, and I also looked at accuracy. And accuracy also I chose because it's so easy to understand. Everybody understands you when you say that your model has an accuracy of 90%. If you say it had an RMSE of 2.98, yeah, it's just less intuitive. Okay, before we go to the evaluation of the performance, let's see how good the predictions of the different models were. Here you can see the quality of the predictions on the training set of the linear model. You see the first 50 movies in the database, and the blue line indicates the real revenue, and the orange line the predicted revenue by the linear model. And I guess overall, not a bad performance. The model misses a few, yeah, by quite a lot, but on average, I think it's reasonably accurate, but that's on the training set, so the revenue was known. If you then look at the validation set, Um, yeah, the performance is almost the same. So I guess the model fits the data quite well. Um, I then went on with the random forest regressor model. Again, you're looking at the predicted and actual revenue of the first 50 movies in the database. And you can immediately see that the random forest regressor is, yeah, at least on the training set, is much more accurate than the linear model. But when you then look at the performance on the validation set, yeah, the predictions become a bit sloppy. It seems to miss movies that didn't generate a lot of box office revenue. And then I compared the two the machine learning models to a neural network, which you see here. And yeah, what you can see here, that it's on the training set, the neural network is yeah, almost perfect. The predictions are well, spot on. But if you look at the performance on the validation set, yeah, they seem to become a bit random. So yeah, I think it's safe to say that the neural network heavily overfitted the training data. So what were the metrics of the different models? Here you can see the R squared measure for the different models. Yeah, you can here you see that the neural network almost was perfect. The R squared score was 0.99, so almost perfect in its prediction. But on the validation set, the R squared was only 0.29. And the same goes for the random forest regressor. The R squared on the training data was 0.94. And for the validation set, it was quite acceptable. It was 0.55. But yeah, the linear regression model I think performed best on the R squared metric. And you can see the same in the RMSE. On the training set, yeah, the neural network almost didn't make an error. And on the validation set, it made the most errors. You can also see here the model for a linear PCA. What I did is I tried to reduce the number of features with a principal component analysis. And I could reduce the 79 features to 45 features. But as you can see, this didn't improve the performance of the linear model. R squared stayed practically the same, so I decided to continue with all the features. And then finally, the accuracy of the three models. Well, it turned out that the linear model actually was the most accurate. The accuracy was almost 90%, but the random forest model also had quite a good accuracy. It was around 88%. Well, the last thing I wanted to know was which features were most important in the linear model. And to answer this question, I had to go back to SPS Modeler because I couldn't find I just couldn't find out how to get feature importance in Scikit. Well, first of all, it was good to see that the R squared metric was the same when you build the model in a modeler. And it turned out that budget was the most important feature to make a prediction. So I guess the old saying, with money you make money, is definitely true for the movie industry. So in conclusion, yeah, the neural network and yeah, to a lesser extent, the random forest regressor overfitted the training data. And for the neural network, I was yeah, a bit surprised by the extent of this overfitting. The linear model and the random forest model performed almost equally on the validation data. So I used these models to make my prediction on the unseen Kaggle dataset. And on the unseen dataset, the roles were reversed. Here, the random forest model made a slightly better prediction than the linear model, but the difference was just 5 places in the ranking. Okay, that's it. Thank you for watching.